So, in the last module we discussed correlated branch predictors, which is an example for two level branch prediction, and now in this module we are going to discuss tournament branch predictor, which is also another example for two level branch predictors. And in the case of correlated branch predictors, we consider a local history table and the local prediction table. Each entry in the local history table is going to keep track of the outcomes of all the branches which are mapped to that particular entry. This correlated branch predictor cannot exploit any information about other branches which are mapped to a different entry in the local history table. So, in order to come up with a mechanism which uses the outcomes of other branches to predict the outcome of a different branch, we can use this tournament branch predictor. So, here in this tournament branch predictor, we actually consider the local history table as well as the global history. This local history table always keeps track of the outcomes of all the branches which are mapped to a single entry, but the global history is going to keep track of the outcomes of all the branches that are executed so far. So, effectively it combines both the local and the global branch predictor behavior to come up with a better accuracy prediction mechanism. So, this is implemented in alpha 21264 processor, and after that there are several other processors also used a variant of this tournament branch predictor mechanism. So, the organization of this tournament branch predictor is something like this. It consists of a local history table, the local prediction table, the global prediction, the choice predictor, and there is a global history register. So, this global history register is going to keep track of the outcomes of last few branches which happen in the program, and these branches can be same branches or different branches. But whereas in the case of local history table, it is going to keep track of the last few outcomes of the same branch. Here we are considering this design whatever is implemented in alpha 21264, so which has 1024 entry local history table, and each entry is having 10-bit information. So, because a local history table has 1024 entries, so we use 10 bits from our branch instruction and index into this table to get one particular entry, and which is going to give another 10-bit information, and this 10-bit information we use to index into this local prediction. This is going to give a 3-bit outcome, and using the 3-bit outcome will make a local decision, because whatever the decision we are going to, whatever the prediction we are going to make from this local prediction is because of the behavior whatever we observed for the similar branches which are mapped to the same entry. So, in other words, this local history table is going to store the last 10 outcomes of the similar branches. When I say branches similar, these branches have their LSB 10 bits same. So, once LSB 10 bits of branch address is same, they are mapped to the same entry in the local history table. So, as a result, all the similar branches are going to map to the same entry in the local history table, and so this entry is going to give the last 10 outcomes of all these the similar branches. And using this, we are going to index into the local prediction table, and whatever the prediction we are going to make from this table is because of the outcomes of the similar branches. So, as a result, we call it as a local prediction. So, this local prediction table is going to give us 3-bit information based on the 10-bit outcome whatever we get from this local history table, and once we have that, we give that value to this mux, but we are not going to make the decision immediately, and we are going to consider the decision coming out of this global prediction table also, and based on that we are going to take a decision. And here this 12-bit global history is going to keep track of last 12 outcomes of all the branches, whether the branches are similar branches or different branches. It is going to keep track of the latest 12 branch instructions executed by the program. And using this 12 bit, we are going to index into this global prediction table, because this global prediction table has 4K entries. So, using 12 bit we index into this, and we map to one particular entry, and that entry is going to give us a 2 bit information, and this 2 bit information is again is going to give us the outcome in a global sense. Each entry in the local prediction table is mapped to 3 bit dynamic branch predictor. So, accordingly, based on this value, we are going to say whether the branch is going to take place or not. If the value is less than 4, then we say the branch is not going to take place, and if the value is 4 or more, then we are going to predict the branch is going to take place here. Whereas in this case, each entry in this global prediction table is mapped to a 2 bit dynamic branch prediction, and if the value is 0 or 1, we predict that the branch is not going to take place, and if the value is 2 or 3, we are going to predict that the branch is going to take place. So, based on this 12 bit global history register value, we are getting one entry from this global prediction table, which is going to give us 2 bit information. And now, if these 2 entries are giving the same prediction, then we will just proceed further, and then we will consider that as the final branch prediction. So, that means, like for example, if this is going to give a value which is more than 3, so that means like we are going to predict the branch is going to take place according to this local prediction, and similarly, if this is also going to give us a value either 2 or 3, then global prediction mechanism also going to predict that the branch is going to take place, because both are predicting that the branch is going to take place, then we will consider that as our branch outcome and proceed further. On the other hand, if this is going to predict that the branch is not going to take place, and similarly this also is going to predict that the branch is not going to take place, then in that case also both are agreed in their decision. So, we just consider that as our final decision and proceed further, stating that the branch is not going to take place for this particular branch. But sometimes the local prediction unit says that the branch is going to take place, and global prediction table says that the branch is not going to take place, or the other way. If this is going to say the branch is not going to take place, and this says the branch is going to take place. So, whenever these 2 tables are going to give different predictions, then we have to consult the choice predictor. The choice predictor also consists of 4K entries, and each entry is having a 2 bit information. And if the value of this choice predictor is 0 or 1, then we will go by the local prediction decision. If the value is 2 or 3, we will go by the global prediction decision. So, using that we will make a prediction, and every time based on our branch address, we take the last 10 bits of the branch address and we index into this local history table. We get the last 10 outcomes of the similar branches, and we index into this local prediction table, and this is going to give us the prediction outcome. And similarly, we use the last 12 branch outcomes of all the branches executed till this point, and we use this to index into this global prediction table, and which is going to give us a 2 bit branch outcome, and based on that we will going to make a branch prediction. And after the branch is resolved, then we will update the local history table by pointing to the appropriate location in this, and then we shift that value into the corresponding entry. And also based on the outcome, we are going to change the values of this local prediction entries, and similarly the recent outcome whatever we got, we insert into this global history table also. Effectively, the LSB bit will be pushed out, LSB bit in the global history register will be pushed out, and the new outcome is inserted at the MSB position in this 12 bit register. And also we are going to update our global predictions, and similarly the choice prediction whenever there is a choice prediction is involved in taking the decisions. And so, this is the overall operation we do with the tournament branch predictor. So, in summary, in order to work with this the tournament branch predictor, we will consider set of tables. One is a local prediction table, and branch is predicted to be taken if the value of a 3 bit saturation counter is greater than or equal to 4, and the global prediction table also is used in this tournament branch predictor, and a branch is predicted to be taken if the value of a 2-bit saturation counter is greater than or equal to 2, and the prediction is made if both the local and the global predictions are the same. If there is a conflict, then we are going to take the help of choice predictor, and the choice predictor is going to choose the decision from the global prediction table if the value of a 2-bit saturation counter is greater than or equal to 2, otherwise it is going to take the decision from the local prediction table. Having discussed this tournament branch prediction mechanism, now we are going to consider an example to illustrate the effectiveness of this mechanism. So, here for this example we are considering 8 entry local history table, and each entry in the local history table is having a 3-bit information, and we also consider an 8 entry local prediction table, but each entry in the local prediction table is having 2 bits, and we have a global prediction table which also has 8 entries and each entry is having 2 bits, and there is a choice predictor which also has 8 entries and each entry is having 2 bits, and we consider 3-bit global history register. And so, we are going to make the prediction for a given branch based on the decisions provided by the local prediction table and the global prediction table, and also taking the feedback from choice predictor table. In order to illustrate the tournament branch prediction, we consider 2 branch instructions whose LSB 3 bits are not same. Effectively, these 2 branches are pointing to 2 different locations in our local history table. By the way, so we are not resetting these values, so we are showing each entry is having different values and so on. This indicates that the tournament branch predictor is already executed few branches, so that is what is indicated by this. So, now we start from a particular time where already these counters, these tables are filled with the different values. Now, we will consider a new branch instruction whose LSB 3 bits are 100. When we consider this branch instruction, so now we are indexing into this local history table, and this has 0, 1, 1. So, that indicates that we have to go to local prediction table to the 3rd location. So, this is 0th location, 1st, 2nd and 3rd location, and this 3rd location is having a value 10. So, according to our 2-bit dynamic branch prediction mechanism, if the value is 2 or 3, we are going to predict that the branch is going to take place. So, this is going to predict that the branch is going to take place, and similarly our current the 3-bit GHR has a state 110. So, effectively this is pointing to the 6th entry in our 8 entry tables. So, we are going to go to the 6th entry in the global prediction table, and which also has a value 10. So, this also again a 2-bit dynamic branch predictor. So, effectively we are going to predict the branch is going to take place according to this GPT also. So, both are going to say that the branch is going to take place. As a result, there is a match in their decisions. So, we are going to predict that the branch is going to take place and we proceed further. If we assume that in reality the branch is taken, so as a result we are going to now update these contents, because the branch is taken and these 2 predictors are predicted that the branch is going to take place. So, we have to update these values. So, now we change the value, previously it was 10, now we change that to 11, and similarly here also it is a 10, we change that value to 11. And also we are incrementing the choice predictor value also to incline towards the global prediction. And after that, now we have to insert this latest outcome into the corresponding the history tables. One is the local history table, the other one is the global history register. So, here we have 0, 1, 1. Now, after inserting this 1, it will become 1, 0, 1, and similarly it was previously 1, 1, 0. Now, after inserting the latest outcome, it will become 1, 1, 1. So, this is the state of different tables at the end of the branch is completed. Now, we will go to the next branch, which is actually pointing to a different location in our LHT, because the LSB 3 bits here are 0, 1, 0, which is different from the previous instructions LSB 3 bits, that was 1, 0, 0. So, once this is 0 1 0, so we are indexing into the second entry in our local history table, which has a value 0 0 1, and once this 0 0 1 is there, so we will go to the first location in our LPT, and this has a value 0 1. So, 0 1 indicates that branch is predicted to be not taken, and similarly the global history register has a value 111, which is 7. So, we are pointing to the 7th entry in our global prediction table, which has a value 0 1. So, this also predicts that the branch is not going to take place. So, both are 0 0. So, they are matching in their decision. So, we are taking the decision as it is. So, we are predicting that the branch is not going to take place here. And now we will see what is the actual outcome of this branch. So, the actual outcome is not taken. So, this is effectively in line with our prediction. So, now once the branch outcome is there, now again we have to do the necessary updates in our tables. So, previously it was 0 1, now we are decrementing that to 0 0, and similarly here 0 1 is decremented to 0 0. And so, we are updating this CPT to make it tend to the local predictions. And finally, we have to insert this value into our LHT and GHR. So, after that it will become 0 0 0 here, and it will be 0 1 1. So, after this, now there is a next branch. This branch is same as the branch we already executed, and so as a result it is now pointing to the 4th entry in the LHT, and which has a value 101 now. So, once it has a 101, we are pointing to the 5th entry in our LPT, and which has a value 0. So, that indicates that according to our local prediction table, the branch is not going to take place. We give that value to the mux, but our global history table has a value 0 1 1, which is a 3. So, we index into the 3rd entry in our global prediction table, and the 3rd entry in the global prediction table has a value 1 1. That indicates that this is going to be taken. So, effectively according to global prediction table, the branch is going to be taken place. So, this has given a value 0 and this has given a value 1. So, now which one we have to select, whether we have to go by the local decision or by the global decision. So, for that we are going to take the help of the CPT, and the choice predictor is now indexed using this GHR value, that is 3. So, we take the 3rd entry in this CPT, and the 3rd entry in the CPT is showing the value 2. So, which is more than 1. So, for any value which is 2 or 3, for any entry in the CPT, if the value is either 2 or 3, we have to go by the global prediction decision. If it is 0 or 1, we have to go by the decision of the local prediction. Since the value is 2, so we will take the decision based on the global prediction. So, and this is what we are going to predict. So, effectively we predict that the branch is going to take place for this the branch instruction, and now see what is the actual outcome of this branch, and this is also taken. So, effectively our prediction is correct according to the branch outcome. Now, we have to update the contents accordingly. So, once it is taken, so we have to change this value, and so the previously the value was 0 0, now it is changed to 0 1, and here the previous value is 1 1, but so 1 1 is because we are considering a saturation counter. So, there is no change in the value here, and since our decision is correct and also the decision is taken based on the global prediction. So, we are updating the choice predictor entry to incline towards the global prediction. So, previously it was 1 0, now we increment that to 1 1, and so after that we insert this prediction outcome into the corresponding entries in LHT and GHR. So, previously it was 101, now it becomes 110, and similarly here previously it was 011, and now it becomes 101. So, this way when we have different branches, when I say different branches, the branches which are not mapped to the same entry in our local history table. So, we can map to different locations in our LHT, and also we can exploit the global outcome of all the branches, and using this global history register as well as the global prediction table combined with our local history as well as the local prediction tables, we can make a proper decision to come up with high accuracy the predictions. So, this is about the tournament branch predictor, and there are plenty of branch predictors proposed in the computer architecture domain, mainly because of the importance of these branch instructions with respect to the system's performance. So, having discussed this couple of the advanced branch predictor mechanisms, now we are going to look at the branch target buffer. So, as I mentioned earlier, in order to deal with the conditional branches, we need two components. One is the branch prediction mechanism, the other one is the target address identification. So, first part, to deal with the branch prediction mechanism, we already discussed various branch prediction mechanisms, and to get the predicted target address, we have to go for the branch target buffer. So, the branch target buffers are going to be implemented using a cache like structure. So, the role of branch target buffer is going to supply the address for a predicted branch. If a branch prediction mechanism says that the branch is going to take place, now the branch target buffer is going to supply the predicted address for that particular the branch. So, using the predicted address, we fetch the instruction and then proceed further. So, as I mentioned earlier, it is a cache like structure to store the last seen target address for a given branch, and this branch target buffer is accessed along with accessing the branch prediction unit. We give the branch address as an input to the branch prediction logic. At the same time, we give this as an input to the cache like structure associated with the branch target buffer, so that we compute these two things simultaneously and we overlap the computation time, and finally at the end, when the branch prediction mechanism makes a prediction that the branch is going to take place, then we will get the target address from the branch target buffer. So, the organization of this branch target buffer will be something like this. So, this is the branch target buffer, and it can be organized as a set associative cache, and each set consists of multiple the target addresses. By using this branch target buffer, we get set of tags for a selected set by using this address, the branch address, and after that each of these tags are compared with the tag of this the branch address, and once there is a match, we are going to consider that as the corresponding target address as the target address for the branch, provided the branch prediction logic is going to predict that this particular branch is going to take place. The output from the adder is going to give the next address to this branch, and the output from this logic is going to give the target address, and the select input for this mux is the outcome from this branch predictor. If the branch predictor is going to say that the branch is going to take place, then the value will be 1. So, effectively we are going to take the target address here. If the outcome from the branch predictor logic is 0, then we are going to take the next instruction in the sequence. So, that will be supplied as the target address, and we proceed further with that. And note that because this is working like a set associative cache, our branch address is also considered as the set index field, the tag field, and so on. So, we apply the set index field as an input to the set decoder to identify one particular set, and the tag field in this address can be compared with the tags of the selected set, so that we can know whether there is a hit for this particular branch. If there is no match in this particular thing, then we are not going to get the target address if the branch is predicted to be taken place. In that scenario, we have to wait for the target address to be calculated. By the way, once a branch outcome is resolved and the target address is computed, we will come back to this branch target buffer and we update the entry accordingly, because we know that this branch target buffer is actually storing the last chain target addresses for the branches. So that the next time if the same branch occurs, then we can use this target address if the branch is going to take place. So for that reason we have to update this branch target buffer after the branch is resolved and the target address is computed. So with that concluding this discussion on advanced branch prediction mechanisms as well as our discussion on branch target buffers. And with that we are concluding this module, and in the next module we are going to discuss the dynamic scheduling used to exploit the instruction level parallelism in superscalar processor designs. Thank you.